Have you ever stopped to think about how physicists can even begin to describe a wave? I mean, it's constantly moving, it's wiggling up and down. How do you pin that down with math? Well, today we're going to dive into the one single master equation that does exactly that. So, what makes a wave so tricky? Well, it's because it's doing two things at the exact same time. It's moving forward, right? Traveling through space, but also every single point on that wave is oscillating, moving up and down. It's this incredible dance between space and time. And that leads us to the big question, right? It moves, it wiggles. How on earth can we capture all of that, this dual motion, with just a single piece of math? I mean, it sounds kind of impossible, doesn't it? But as it turns out, physicists came up with a solution that is just incredibly elegant. And that solution, well, it's all packed into what we can think of as the wave's master equation. This thing is literally the key that unlocks everything we could ever want to know about it. And here it is. This is the hero of our story today. This is the progressive wave equation. Now look at that. This one beautiful piece of math can tell you the displacement, that's y, for any position x along the wave at any moment in time t. It's a totally complete description of the wave's behavior. Okay, I know what you're thinking. That looks a little intimidating, right? All those symbols. But don't worry, each one has a very specific and actually pretty simple job to do. We've got A for amplitude, K for the angular wave number, omega for angular frequency, and phi for the phase. We're going to break them all down one by one. All right, so to make this easier, let's start by kind of hitting the pause button. Let's freeze time for a second and just look at the physical shape of the wave. We'll call this our snapshot in space. So the first and honestly the most straightforward part of the wave's shape is right there at the very beginning, that letter A. And A, as you might have guessed, stands for amplitude. To put it simply, this is just how big the wave is, how tall are its peaks, how deep are its troughs. It's the maximum distance it moves from that center equilibrium position. So if you look at a picture of a wave, the amplitude is just that distance from the center line all the way up to the highest point, the crest, or all the way down to the lowest point, the trough. It's what tells us about the wave's intensity, its energy. Okay, next up in our little snapshot here is K. This is the angular wave number. And this one is all about how bunched up or stretched out the wave is in space. So you can think of K as a kind of spatial frequency. Instead of telling you how long a single wave is, K tells you how wavy it is over a certain distance. It basically describes how quickly the wave wiggles as you move along it. It's measured in radians per meter, which is just a really convenient way for physicists to talk about cycles when they're working inside a sine function. And here's the key connection. This K value is directly tied to a concept you're probably more familiar with, wavelength, which we represent with the Greek letter lambda. And here's the deal, they're inversely related. So a really long, stretched out wave is going to have a small k, and a short, scrunched up wave, that will have a really big k. Okay, so we've got the shape down, that's our snapshot. Now, let's hit the play button, unfreeze time, and figure out the parts of the equation that tell us about the wave's motion, its story in time. And the absolute key player when it comes to motion is this guy right here, the Greek letter omega. This stands for angular frequency. So if K was all about how the wave changes over space, omega is all about how it changes over time. Imagine you just stood in one spot and watched the wave go by. Omega tells you how fast that single point is bobbing up and down. You can almost think of it as the wave's internal clock, ticking away in radians per second. And yeah, you guessed it, just like K was connected to wavelength, omega is directly connected to the period, t, which is simply the time it takes for one full wiggle to happen. And again, it's that same inverse relationship. A wave that oscillates really slowly has a long period t and a small omega. Makes sense, right? All right, enough theory. Now for the fun part. Let's put this equation to the test and see how it all comes together. We're going to take a real-world example and just pick it apart. So here's the problem we're given. We've got a wave traveling along a string, and its motion is perfectly described by this specific equation you see here. Our job now is to use what we've learned to pull out all its real-world physical properties. And this is where it gets really simple, almost like a puzzle. All we have to do is map the numbers in the problem to the variables in our general equation. We just line them up. So right away we can see that the amplitude A is 0.005 meters, the wave number K is 80, and the angular frequency omega is 3.
It's that easy.
And once we have those key values, everything else just falls into place. We can plug k into our formula to find the wavelength, lambda, and boom, we get 7.85 centimeters. We plug omega into its formula to get the period, t, and there it is, 2.09 seconds. And from there, finding the frequency as a snap, it's just 1 over the period, so that's 0.48 hertz. See? It all just flows right out of the equation. But here's where the real magic happens. The equation doesn't just give us the general stats of the wave. It can tell us something incredibly specific. So let's ask it. What is the exact displacement of the string at the 30 centimeter mark at the precise moment of 20 seconds? Let's find out. So you just plug in those numbers for x and t, you run the calculation, and the answer? 5 millimeters. Just like that. The equation tells you exactly where that piece of the string will be. That is the power of this thing. So let's just step back for a second. The big takeaway here is this. We started with what seemed like a super complex problem, right? This thing that wiggles and moves at the same time. And it turns out this one single elegant equation holds everything. It tells us its height, its length, how fast it wiggles, and its exact position, anywhere at any time. It's all in there. Now look, we've just been talking about a simple wave on a string. But this mathematical blueprint, it's so much bigger than that. So I'll leave you with this question. What does it mean that the very same fundamental equation can describe the sounds you're hearing right now, the light that lets you see, and even the incredible ripples of gravity traveling across spacetime? It's kind of amazing, isn't it?